Professor Karl Leo from the Technical University of Dresden, who's right now on sabbatical at the King Abdullah University of Science and Technology in Saudi Arabia, where he heads the Solar Center. With this brochure, of course, you have already learned quite a bit about Karl. I'd like to emphasize that Karl is a very special person in the sense that at the same time he has the highest academic reputation for his fundamental work on organic light-emitting diodes and organic solar cells, but also he is one of the few folks that have been able to transfer the technology into highly successful companies. For instance, Novaled in the case of organic light-emitting diodes, Heliatech in terms of OPV. I'm sure, Karl, that you'll say a few words about that, so I'll leave it to you to say more. Karl, as you see from the leaflet, also has been rewarded by quite a number of prestigious prizes, and there is one that's not on the list that he received actually last week from the Hector Foundation in Germany. Hector is one of the 5 co-founders of SAP, and he is now also an Hector Foundation Fellow. So with that, I'd like to leave the floor to Karl, and we'll be looking forward to an exciting presentation. Thank you again for being with us.
Well, thanks for the very kind introduction and the invitation to present here. I was very impressed to see Georgia Tech, and I had very nice discussions today. As you might notice, maybe not from the distance, I'm even wearing a Georgia Tech tie, which is actually caused by the simple reason that my luggage got lost when I arrived this morning at the airport. So Jean-Luc gave me this tie with the bee. Is it a bee? Yeah.
No, not a bee. That's a yellow jacket. So we still have to teach a few things, but we'll do that later.
Okay. So I'll talk today about organic solar cells, which is one of the many nice things you can do with solar cells, but I'll take the liberty to show a few slides of what I'm doing currently at KAUST in Saudi Arabia. It's as you probably know, a very new university. Actually, can we dim the light a little bit in the front too?
I think we can.
Oh yeah, perfect. So my office is up there with a nice view on the Red Sea, and I'm currently setting up the solar center, and that's how I look at work usually. And this in the back is once more, there's my office here. This is a view from the harbor. Now the Solar and Photovoltaic Engineering Research Center, as it's called, has at the moment 8 faculty. We are hiring additional faculty. It has very extensive laboratories and a very nice clean room. What we want to do is to bring world-class photovoltaics research to Saudi Arabia. It's an ideal country for this. Later on, we'll also work on storage and conversion and train the people for this technology. And I think the unique point about the Solar Center at KAUST is that we have a very broad array of emerging PV technologies, organics, perovskite oxides, and quantum dots, and also some copper, indium, gallium diselenide work. And in another special point is that for several of these materials, we combine either vacuum processing or liquid phase deposition, so that you can understand the difference in these 2 things. Okay, but now let me come to the main talk, and I start with thanking the people who were involved in this work. This is a joint work of TU Dresden. I'll present several results from Johannes Wittmer, from Chris Elschner, Christoph Schönemann, Wolfgang Dress, and Martin Hermenau. And this is done in collaboration with the company mentioned, Heliatech, with Peter Börles group in Ulm, and a little bit I'll talk about modeling of in the group of Denis Andrienko, but this will be only very brief in this talk. Now, if you look at organic semiconductors from a product perspective, there's one very successful product. This is the small mobile phone display I'm carrying once in my pocket, and it made me from a taxpayer spender since 2 years ago to a tax money generator. You know, and this is for me at least, it was a very nice point when I was able to go to an electronics shop and show to my kids what I'm doing. Now, what will be the next step? I think we'll see very soon the large TVs. There are first TVs on the market, but the pricing is prohibitive. OLED lighting is a difficult field in terms of efficiency and pricing. The hurdles are very high. I also see organic PV still as a difficult field. I'll explain the reasons in a second. And maybe, unfortunately, the most difficult field is organic electronics, transistors, logic, because there the competition from silicon is sometimes overwhelming. So step by step, I'm sure we'll see more products, and maybe in 20 years we'll have all these electronics around us in every day, in our jackets, in our cars and everywhere. Now, when we come to organic photovoltaics, the potential is immediately clear. It's a flexible technology. It's a potentially transparent technology. It can have different attractive colors. So in many respects, it's a very nice technology. It should be low material and energy consumption, short energy payback time. And at the end, the pricing should be very attractive. Unfortunately, most of these potential points are not really realized, and for several reasons, we still have to work a lot to really meet the expectation. The one issue with this organic PV is that when you look at this NREL plot of the efficiency of photovoltaic systems, the organics is still down here in the noise, so to speak. As you can see, there's a large gradient, but still we are in the 10% range with efficiencies. And the established photovoltaic technologies are in the laboratory at least well above 20%. Now the other big issue is, as you know, the pricing, and there's a learning curve which says that when you double production, price goes down by about 20%, and with some oscillations this is now followed for 30 years, and especially in the last few years we actually went under the average. And there are very reasonable projections that in the next 5 years or so, silicon modules will go down to 40 cents per watt peak. And this is a price which many people never thought to be possible with silicon, and the question is there any space left for organics? And the answer is yes, but it's not easy. The question is, what do we need to do to make organic PV successful? If you go to conferences in organic PV, many people start their talks with statements like, you know, if we make it cheap enough, efficiency is not that important. Or I've heard statements, you know, 5 years lifetime is okay. If it doesn't last longer, we simply exchange the modules. I doubt that very much. I would say the minimum we need is 15% in the module, more than 20 years lifetime, and well below 50 cents per watt peak. And the key point actually is the efficiency, because efficiency pays off in many respects. Efficiency reduces the cost of electricity generation clearly, but it reduces the energy payback time, and it also helps to realize this on small area. Sorry that I start a little bit more extensively with economic points, but I simply want to show where the challenges are. This is a paper which was published a few years ago, which calculates the cost estimates for organic PV, and as you see, per square meter, depending on whether you are aggressive or less aggressive, you have $20 to $40 approximately per square meter. Now imagine you have a 5% module, then even with the aggressive estimate, you are already more expensive than silicon. So at low efficiency, there's no way to go. When you look at the numbers, for instance, for the moment, when you buy an organic material for production, you don't pay $2, you pay $200. So this is pretty much, both estimates are pretty much aggressive. And as said, the total shows you that even for pricing, you need high efficiency to keep the area small. The other point is energy payback. This was published in a nice paper in 2012. It shows the harvesting of a module versus the efficiency, and this is what you harvest typically in Germany, maybe in Atlanta twice as much or significantly more. But the basic message is that organics is quite good compared to various inorganic technologies. But even at low efficiencies, you still have several years at least under German circumstances. However, this curve clearly goes 1 over x, and you can see if you go to 10 or even 15%, then you reach very, very short payback times, which can be even in Germany on the order of 2 or 3 months. So again, this is an argument for high efficiency. Now, if you look at the efficiency predictions for organics, we did some calculations in Dresden, the PhD thesis of Toni Müller, and the basic result was that for a single junction cell you can reach something like 15% as maximum efficiency, which means you have 10 to 12 in the module, which tells you immediately that with a single junction cell, organics probably doesn't really reach ever a market. And the way to go is, like discussed recently in a paper by Michael Gretzel, to harvest with several junctions a larger part of the solar spectrum, and you go then from the Shockley-Queisser limit of 31% for a tandem to 42 and for a triple to 49. And another point is that when you go to tandem or triple, you actually reduce the current, and therefore you have lower electrical losses. So we need to go to tandem or even to triple, and when you go to tandem, we did again some calculations, you find out that something like 20% is absolutely reasonable. And that's the way to go, and that's also my personal goal, say, to reach in the next 10 years efficiencies of 20% in the laboratory. And as you know, the progress has been enormous. We started with Jing Tang's result at Kodak of about 1%, and now the certified and larger cells in the last few years have from about 3% to Heliatech now at 12%. Taken an enormous development, and that is really the question, how long can we continue that and how much time will it take to come to this 20%. Okay, but now after this somewhat lengthy introduction, let me come to the science, and the biggest challenge in my opinion in organic PV is to find the right materials, because the search for materials is difficult, and there are many properties which need to be met. Why is it difficult to find materials? Well, an organic solar cell has a somewhat more complicated chain of events from absorption of a photon to charge extraction. You don't generate immediately carriers, but excitons, they have to diffuse to a heterojunction because they have to be separated here at a heterojunction, and then you need to transport again, in this time the charge, and then you need to extract it. And the working structure, as you probably know, is more complicated than a traditional solar cell because you have to have a heterojunction. The one issue is the diffusion length. These are some measurements we did in Dresden some time ago for a perylene derivative as a model material. And by changing the layer thickness and modeling it, you can very precisely determine the exciton diffusion length. And the very disappointing result is that it's about 10 nanometers. And this is very typical. There are some materials which might have a little more, some have a little less, but for the moment we have typical numbers like this. Whether this is extrinsic or intrinsic is not known. And it's a good question whether we can raise that, for instance, by a more highly pure material. The other issue is the fact that the exciton is very tightly bound. This is a nice diagram from Moritz Riede, which shows an organic exciton, which is basically a nanometer or so large. It's on one molecule, and its binding energy is something like 10 times kT, compared to an exciton in silicon or gallium arsenide, which is 20 nanometers or so large, and is much less than kT. You have a problem here. You cannot really separate the charges. Now the way to proceed is known since many years. The first discovery was from Jing Tang, who had the idea to use a heterojunction to separate electrons and holes. So the excitons diffuse to this heterojunction get separated. Now because the excitons do not like to diffuse, you can also bring the junction to the exciton. And this is done in the bulk heterojunction, which was actually, many people overlook that, invented by Hiramoto in Japan already in 1991. And this way, using this morphology, you can get the junction to the exciton. So at the end, what we do have is a nanomorphology of domains of a donor and an acceptor material. The energetics must be okay. The transport in this morphology must be okay. The orientation of the molecule must be controlled. And this altogether is a very difficult and challenging issue, as I'll show you in some details. Now, when we come to organic PV, there are kind of two schools. The school I'm, so to speak, member of is the oligomer or small molecule school, which is either done by vacuum or by solution processing. And the other school is the polymer school, which is done usually by solution processing. The physics at the end are very similar, but in many respects there are differences in processing. For the moment, I personally believe that the oligomer approach has advantages. As you know, in the mobile phones, we talk about oligomers for the same reason. These materials have a fairly simple synthesis with defined molecular weight. We can purify them simply. And in these molecules, we always use the pure fullerene C60, which is very cheap and easy to obtain, whereas most of the polymer results are actually usually done with PCBM or C70. Now, nevertheless, to give you a flavor where we are, I cite some literature results for high efficiency polymers. There are some proprietary results beyond 10%. There's an open paper which I found, which has been published in Nature Photonics, and which reported also results above 9%. And as you can see, these are fairly good solar cells with also fairly good external quantum efficiency. In the small molecule field, there's also a lot of work on materials, and people have explored a larger zoo of materials, benzoporphyrins, squarenes, merocyanines, body P dyes, and thiophenes. I will in the following mainly talk about thiophenes, because that's where most of the work was done, and this is the compound class which Heliatech is using. But it looks like that there are many molecules which work, and there's not really a criterion why a certain materials class is better or worse. Again, in the small molecule field, people have either used solution processing or evaporation, and solution processing has here some advantages, like you can actually make fairly thick active layers. As you'll see in my experience, they are much thinner, because you can make good transport properties. Especially this results from the Bazan group showed that by adding an additive, you can control the morphology, and by using a suitable concentration of additive, the morphology is obviously much better and the cells are much better. And there are some recent results. I found a result with more than 8% now using C71 PCBM. And the most recent result is now from Nature recently, from Yang group, which had for a tandem cell at 10%. So for the polymers, the numbers are quite good and are almost as good as for the small molecules. Now let me come in more detail to which materials we need. We have this bulk heterojunction, and what we need to do is we must form a network with high and balanced mobilities. We must adjust the domain sizes to have at the same time good separation and good transport. And the calculations show that we need mobilities of about 10 to the minus 3, which sounds fairly low, but actually in this bulk heterojunction is already a pretty high value. Now, even the fact what an optimum mobility is not clear, and I want to discuss that with some results I'll show you in a second. But the key challenge at the moment is actually that ideally we would define a solar cell by designing a high efficiency device, and then we would go this way. We would go back and tell the synthetic chemist, please make this and this molecule to have the right properties. At the moment we go the other way. We make a molecule, go all this way, and then we judge the quality of the molecule. And I'll show you later in my talk that going this way is very difficult, because the device you get at the end is not only depending on the molecular structure, but also in much detail on how you process the devices and what the conditions are. Now, once back to this mobility question, these are some calculations Wolfgang Tress did in his PhD thesis. He made a drift diffusion model and calculated a simple bulk heterojunction device, and he used some different recombination models, a very simple direct bimolecular recombination model, and a somewhat more involved Langevin model, which is probably more appropriate for organics, where the diffusion of the carriers is also important. When he uses the simple recombination model, it actually turns out that the efficiency of the device as a function of mobilities for electrons and holes is increasing and reaches at about 10 to the minus 3 a plateau. So then you are not limited by mobilities anymore. So the basic conclusion would be you have to have 10 to the minus 3 and better in mobilities. Now, if he takes the more appropriate Langevin theory, things look more complicated. You again increase the efficiency with mobility, but 10 to the minus 3 is now a maximum. And when you go higher in mobility, efficiency goes down. If you look at the details, it turns out that very simply, the higher mobile the carriers are, the more recombination you have. Unfortunately, we couldn't yet experimentally test this because we cannot reach this regime. We have moved up here, that seems to be true, but we haven't had these high mobility materials to move down. Another issue is actually to measure these mobilities in a bulk heterojunction. Most people measure mobilities using field effect transistors, but that is not what we need, because we need a vertical transport in a device, and we need to know the field dependence and the carrier density dependence, which is typically present in these organic materials. And recently, Johannes Wittmer in his PhD thesis found, in my opinion, a beautiful new method to measure field-dependent and density-dependent mobilities. What this measurement delivers at the end is such a contour plot where you plot the field and the whole density, and the mobility is color-coded, so you can see these dependencies directly. He called this method POEM for potential mapping by thickness variation. The idea behind the model is very simple. Let's assume you have a homogeneous a film of a material, and you transport carriers through it, and now you start to slice, so to speak, this material. When you keep the constant current for different thicknesses, for instance, when you go down for this thickness, you need this voltage, and if you go down in thickness to a thinner sample to have the same current, you actually need this voltage. If you go down here, you need, for instance, this voltage. You can actually plot the electric potential in the sample. What you do is you make a series of samples of different thicknesses, and then you measure always the same current, and the voltages directly tell you the potential in the sample. And from the potential profile, you can get the electric field profile, and from the electric field profile, using the current, you can get the carrier density profile. So what you simply do is you make a derivative of the potential, then you have the field, and then you make a derivative of the field, and this way you can get the density. And if you know the current and the field and the density, you can actually calculate the mobility at each location of the sample. And since you also know the field and the carrier density at this location, you get what you need, that is mobility as a function of field and carrier density. This theory is extremely simple. You don't need a transport model. The experiment is more complicated because you need a certain definition of your sample. What we use is typically PIP or NIN samples, where we have a material under investigation between two doped layers. The reason is that by using that structure, we have defined injection and extraction. That is what you need. Furthermore, you need a symmetric device design because you should not have a built-in field that would disturb this analysis. And clearly you have to have either electrons and holes, or you need selective contacts. And indeed, such a structure to a large degree fulfills all these requirements, and this way we have now a very nice and precise method to determine mobilities. You can check the method, I don't want to go in too much detail, by using a certain transport model and then do a numerical analysis of the IV curves and then do the analysis using his approach. And we tested that and did that with various transport models, and the agreement was very, very good. So we are pretty sure that the model and the approach is correct. I want to show you only one example. This is a bulk heterojunction of a zinc phthalocyanine derivative with C60. And what you basically observe here is that in this material there is a quite pronounced field dependence. If you go for a constant carrier density to higher fields, you see that the mobility is significantly increasing. Whereas if you go at a certain field to higher carrier densities, you can see that the color code is virtually unchanged. So there's very little field dependence. However, in that measurement, the density was somewhat lower than it would be in a real device. But given that model now, you are able to analyze the mobilities and look at the very disappointing results. That was a bulk heterojunction prepared under the usual way we prepare a solar cell, and the mobilities are 10 to the minus 6 and not 10 to the minus 3, and that's the main problem we have in these materials. Okay, now in the second part of the talk, I want to come to our investigations of what we call the thiophene zoo. We call it the thiophene zoo because it's full of animals, and these different animals is a very large number of molecules which we obtained from Peter Börle's group. The basic idea is that you have two handles. The one handle is actually the backbone length in thiophene units. We typically look at 3 to 60. And the second handle now is the side groups of the molecule, either simply hydrogen or up to butyl groups. Now what are the effects? This handle actually changes directly the electronic properties of the molecule. This handle does not change the electronic properties, but it changes the crystal packing. But this way again, it changes the electronic properties in the solid state. This is nicely visible. These are simply the energy levels versus the backbone, and as you can see, the LUMO level is fairly unchanged as a function of thiophene units, whereas the HOMO level can be nicely shifted, and this way we can actually shift the energy gradient at the heterojunction. We can optimize the voltage, and it turns out that with the 5-ring devices we have the optimal voltage. However, if you look in more detail now as this energy shifts for the different number of thiophene units, but also for the side groups, and you compare here measurements in solution and in the solid state are the red data, you see that the solution measurements scatter only little as a function of side group. They basically change here by the length, the backbone length, but the solid state results in red, you see they make significant fluctuations with the side groups because you change the solid state morphology. So it is very complicated and very difficult to really control the energy levels. And we have observed, I don't want to go in any detail, but you get completely different crystal structures depending on the side group, and it's not possible at the moment to predict that in any way. So although these materials should allow a systematic variation in practice, when you really do it, you have already an extremely complicated system. I will not talk about voltages today, but I'm actually using one Heliatek slide here to show that for this most recent Heliatek material, which is again now a proprietary thiophene derivative, that the voltages are very good. Basically, what you want is a difference between optical gap and VOC, which is as small as possible. And the Heliatek materials are now, actually, these are not really the best we have today. Today we are at about 0.6 volts between optical gap and VOC, and if you do some theoretical considerations, it looks like that is close to the optimum that what you can do in an organic solar cell. In an inorganic solar cell, you would have something like 0.3. That's what we lose in organics. But now let me come back to the question of crystal structure and morphology. And that we studied in more detail in a paper which we published already 1.5 years ago. We took 5-ring thiophenes, which have the optimum voltage, and we took the methyl side groups. In this case, we used all methyl, but at different locations of the molecule. So a structure called 1, 2, and 3. And when you look at the solution spectra, they look fairly similar. There's a small difference for the materials. The solid state spectra, as you see, are massively redshifted, which they should be. It tells you there's good coupling between the molecules. And here you see the differences become larger, and especially the compound 3 has the largest redshift, which says it seems to have the largest packing. Now, when we looked at the ordering using X-ray scattering, it turns out that there's a quite complicated behavior at room temperature. Compound number 1 has the highest ordering and the most clear reflexes. But at the temperatures where we usually deposit the solar cells, the compound number 3 has now the highest ordering. So those two results this year and this year tend that compound number 3 seems to be the compound of choice. And indeed, at that time when we measured the efficiencies, we noticed that compound number 3 brought the best results. And so the message was clear, okay, this is the best packing and it's the best molecule. That was our conclusion. Keep in mind that when you look at this solar cell of 6.9%, it has an active layer of only 30 nanometers. That is because we have insufficient mobility. If we would have a mobility 1 or 2 orders of magnitude higher, we could do there 100 nanometer and would be well above 10%. But so far we haven't managed that yet. In the meantime, we've done a little better. We reached over 7, and in some internal results, we are now at 8%, but still not really at the potential of the material. However, we have recently revisited that story. We processed once more the materials, and we confirmed the efficiency that the compound 3 was better than the compound 1. But then we looked in more detail at the structure. And for that purpose, Chris Elchner in his PhD did some measurements in Stanford at the synchrotron using grazing incidence wide-angle X-ray scattering. And what he observed is that actually if he took the single layers, 30 nanometers of the single layers, that the scattering images in the synchrotron for both compounds were almost the same. There was a slightly less ordered structure for the compound 1, but it was fairly similar. However, when he then did again measurements of the bulk heterojunction, DCV5 and C60, he noticed that we had overlooked a subtle effect, and that is when you go for the compound 3, for instance, from room temperature to 110 degrees, you see that there's a much higher order at 110 degrees. But absolutely the same effect is happening for compound 1, but at higher temperature. So the problem was that we had overlooked that due to this small difference in the methyl side groups, the materials obviously needed different temperatures for optimization. And the problem is that this compound 1 is already at a temperature which is critical for organic solar cells. So we simply didn't go to that temperature when we did the devices because of diffusion effects. And the whole morphology developed as a function of temperature turned out to be rather complex. At room temperature, you have very small domains with low crystallinity. And when you go to higher temperatures, the domains grow larger. The crystallinity actually wasn't much higher, so the main effect of the better reflexes was a larger domain size. At the same time, the films start to be rough. And at the highest temperature, actually, the films itself were that rough that they couldn't be used for devices anymore, and the efficiency then goes down very quickly when you exceed a certain temperature. We could actually show that at very high temperatures that you were seeing these worm-like crystals, which were pure thiophene, which was kind of growing out of the layers and formed crystals on top of the bulk heterojunction. So the dynamics of this bulk heterojunction formation is a very complex function of temperature. So that's what we learned, and the basic message is it is very difficult to judge whether a certain molecule is good or not and by simply missing some parameters you can come to completely wrong conclusions. Okay, so the final part of my talk I want to spend on tandem cells. As I motivated in the beginning, you need them, and on energy harvesting. And the tandem cell idea is probably well known to you. You basically combine two photoactive materials at different wavelengths. There are now two challenges in these organic solar cells. The one challenge is if you combine two cells, you need a so-called recombination contact where electrons and holes recombine. And the other challenge is, since we have thin film devices, we have optical standing waves, and we need to generate the cells in a way that the standing waves fit to the absorber layers. Fortunately, a couple of years ago, we had published a paper where we do this so-called PIN structure. These P and N layers are high bandgap transparent doped layers. And first of all, they form a PN junction, which is a very good recombination contact. And secondly, you can actually vary the thickness of these window layers beautifully, and you can really adjust that. And this was a key point. And fortunately, also we filed this as a patent, and that is one of the key IPs Heliatech has. It's quite interesting to look at the physics of this recombination contact. That is a diagram I took from an article about 3-5s, and you know the most efficient solar cells we have today are these 3-5 multi-junction cells, which are above 40%, and they use exactly the same principle. They use these highly doped PN junctions. And since I started or did much of my scientific career in basic transport effects in 3-5s, it was really nice for me to come back to these good old days when we looked at more detail at these junctions. This was work which was done by Hans Kleemann in his thesis. He looked at these organic PIN diodes. He made an intrinsic interlayer to really look at these diodes and to control the fields. And what he did is he varied the interlayer thickness and looked at the reverse breakdown. And the basic message was that in the forward curve, this interlayer thickness is not relevant, which you expect for a forward PIN junction. But for the reverse breakthrough, every nanometer, so to speak, counts. And what he did basically was making Zener diodes. So he made diodes which have a very nicely controlled breakthrough and which are actually useful for many applications like memory. The basic point is if you make the intrinsic layers thin enough, say 6 nanometers or less, you get almost symmetric IV curves, and that is what you need for this recombination contact. And he also was able to look at the transport mechanism and could clearly show that this is indeed valence to conduction band tunneling by looking at the temperature dependence. The reverse current is almost not temperature dependent, which you would expect for a tunneling process. And together with the group of Giovanni Coniberti in Dresden, we could actually make a theoretical model. They set up a molecular model where they calculated the tunneling rates from the HOMO levels to the LUMO levels in a fairly simple way. And they fitted our IV curves, and they distinguished two approximations. The one is where the motion from molecule to molecule in this chain is by hopping, and the other where you have a really coherent states over these few molecules. And the somewhat surprising result was that the coherent model fits the data and the hopping model not. So at least on this kind of 1, 2, 3 molecule reverse tunneling, you seem to have coherent transport. You can also analyze the mass of the carriers, and it turned out that we got masses which are way below 1, which was quite surprising. And this result is not fully understood. We've published it, but so far we don't have an explanation for these very small masses. Okay, that was a very short excursion, and I'm coming back now to the solar cells and just show you some results which we published already some time ago, where we did such a tandem cell using a thiophene and again a phthalocyanide, in both cases with C60. As you can see in this case where we use open materials, the overlap is significant. This is not ideal. We would actually need a larger gap between the two materials. But producing this cell is fairly simple. You have two individual cells and you simply stack them on top of each other. What you see here now is that these devices are fairly complicated. you have something like 10 or 12 layers, but using this vacuum technology, this is not difficult to do. And you can nicely double the voltage. You get very high fill factors, higher than for the individual cells. What we didn't really achieve in this case was good current matching because of the spectral properties of the two materials. And working together with Heliatech, we optimized that step by step, and the latest result published by Heliatech is this world record of 12%. As you can see from the voltage, it's already a triple cell, and it shows the potential, but it's not really what is relevant for production. Relevant for production is what they did on modules. These are modules on glass, and already some time ago they had 9%. More recent results is almost 10% for the active area. And that is I should mention that a big difference to the polymer OPV technology, because the current record polymers are all using C71. They use poisonous solvents and a rather complicated synthesis, whereas these materials are C60 and absolutely production ready, and at the moment Heliatech is putting that into products. Now one factor which also helps a lot is harvesting. We call that the O factor. What do I mean with harvesting? When you talk about a solar cell efficiency, you talk about one sun, 25 degrees and perpendicular incidence. That's the standard measurement conditions. However, in reality, typically your modules are much hotter, and not only in the morning and the evening, but if there's bad weather, you have less than one sun and it can be diffuse. And fortunately, organics is in all of these points favorable at higher temperature, less than one sun and diffuse light. We have observed an improvement, and in total we had up to 30% better harvesting. So 12% means that it harvests better than say 15% or so silicon module. To show you part of these data, these are measurements by Heliatech on 10% cells, and as you can see, the organic cell is getting significantly better to the operation temperature, whereas all other PV technologies go down. And same for intensity. If you go down from 1 sun to say 0.2 suns or so, organics go significantly up and all the other technologies go down. And altogether, with an angular effect, you have this nearly 30%. Frankly spoken, however, the better our cells will be, the less this effect will be. Finally, a few comments about lifetime and manufacturing. Clearly, it's a big issue whether these organic materials can be stable enough. And last year, Christiane Falkenberg submitted a thesis on new electron transport materials. She wasn't looking for a long lifetime, but she wanted to replace C60, because we were always speculating that C60 should be a source of instability in organic solar cells. We were actually proven wrong in her thesis. She found some materials which can replace C60 in terms of efficiency, but when she did the lifetime measurement, unfortunately and disappointingly, the C60 still gave the best lifetime results. And she was measuring this under an intensity of 2 suns. We used simple glass encapsulated devices. And stability is defined as a lifetime is a 20% decay. And when she did a very rough extrapolation for her thesis, it would have been, at least under German conditions, it would have been a lifetime outdoors of 37 years. Now this is not really practically relevant because we won't use glass as substrates, but it tells that the intrinsic stability of these organic materials is excellent. One comment is that you first of all need to encapsulate very well. The second point is you need to block UV. If you don't block UV, these lifetimes go down, but in practice you need to block UV, which can be done technically. Also, I want to show a more practically relevant result, which is again taken from Heliatech. There's a so-called standard DMP test in PV, and that means that your molecules, that your modules, not molecules, must survive an 85 humidity test. For 1,000 hours, you should have at most 10% decay, and as you can see, the Heliatech modules had about 3% efficiency drops. So the Heliatech modules now pass this standard test which every PV module must pass. And the real outdoor device lifetimes are now above 10 years on foil. So I'm very optimistic that this 20 years lifetime I've named will be met. Now about production, this production Heliatech is doing, the pilot production is on a roll-to-roll coater. Unfortunately, it's a proprietary tool, and when they introduced the tool at the inauguration of the facility, they made a big paper wall in front of it, so you cannot see anything how it looks really. So I'm not showing you the pilot production tool of Heliatech, but I'm showing you a research tool we are operating at the Fraunhofer Institute in Dresden. And the way it works is quite simple. You have a big vacuum tank, and in that vacuum tank at the door you have here the plastic foil. This is 30 centimeter foil, and you unwind it and pull it around a big cylinder which is rotating. And around this cylinder, not really visible, they are up here, you have the organic sources. These are linear sources, and they are put next to each other. And what you do is you evaporate all these 10 or 12 layers in one run. While you pull around once, you evaporate all the layers. So it's very efficient to coat, and you need only one run around it. The desired speed would be that you reach several meters per minute, and then you can produce these cells very efficiently. And there's one very economically important point. If you scale such a tool with the width of the band, it scales with the square root of the cost scaling is only a square root. So if you go from 30 centimeters to 2 meters, the tool is not really much more expensive. And these are examples not for organic solar cells, but for organic LEDs. And this is actually not a plastic foil, but in this case we used an aluminum foil. You can also do these organic LEDs and solar cells on an aluminum foil, which is mechanically very robust and also a good encapsulation in one direction. So this roll-to-roll production basically works, and at the moment Heliatech is ramping it up. So finally, a slide to the applications, and I brought a little demonstrator to show the key application. If you look at the different markets for organic PV, there is one mobile electronic market, and then the basic result is it's a very small market. You know that there has been a bag with organic solar cells of Konarka, and Konarka went bankrupt, so this probably was also not a very attractive market. The first market where I think we'll see Heliatech product is in automotive, and the key point why people pay a lot of money for a fairly low efficiency structure is transparency. So this is a transparent module. The transparency you need for this application is only about 20%. This is because the projector comes from here, not very good to see, and it's a fairly homogeneous looking quite nice colored cell, and therefore we see the first application in this market. The second interesting market identified by Heliatech is the building integrated photovoltaics. Imagine that you would have in all windows such a foil you would shade and at the same time produce electricity. The market which they didn't dare to make a red square around is what the market I would love to see. That is the power plant market, which is at the moment completely dominated by silicon. I think organics has the potential, but it will be very hard work to achieve the efficiencies and lifetimes for this market. But given the fact that this is only carbon, it would be a beautiful goal to achieve that. So let me come to the conclusions. I think organic PV is, although it has improved a lot, still needs an efficiency breakthrough. We probably cannot work with single junction devices. We probably need at least tandem or even triple structures. The most, in my opinion, most difficult challenge of organic PVs are the design rules for materials. We have a complex donor acceptor heterojunction structure, and to find the design rules is very challenging. And especially the fact that this all depends in a very subtle manner on process variations makes this very difficult. And the manufacturing technologies are there. They haven't been really proven at low price, but it will be possible to manufacture all of that at low price. And the dream is that in 20, 30 years, if you drive through a city or through the countryside, your eye should be always on an organic solar cell. Thank you.
Thank you very much, Karl. I'm sure there will be questions. One of the things that I wanted to ask you is with regard to the point you made a couple of times, but the use of C60 itself. And you made the distinction with respect to not only C70 but also to PCBM. And so is there any issue in having C60 without having some of the soluble side groups?
Yeah, I mean the C60 is produced in a very simple industrial process. You basically create a special kind of soot and then you purify it, and therefore you can project that it will be very cheaply available. That's the biggest advantage of using C60, whereas for the PCBM you need another synthesis step. And especially, at least at the moment, C70 and PCBM's C71 is very expensive, and it's very difficult to clean it. So for the moment it's much more advantageous to use C60.
But is there an issue between C60 and C61 PCBM in terms of the fullerene itself going, into the donor component?
Well, you can change a little bit the energetics of the C60 by choosing the synthesis, the side group for solubility. That's another handle you have, which we don't have. For us, C60 is the benchmark, and we must adjust the donor material to the energy levels of C60. So you don't have this handle. That's an advantage of using PCBM or other compounds.
Seth? Two questions. You commented on the solvent advantage of one approach versus another approach, in the fact that the spin coating uses caustic solvents. Have you guys done an analysis when it comes down to the actual solvent, the amount of solvent that's used in the purification steps of the materials along the synthesis path versus the amount of solvent that's used in depositing the material?
No, it's a very good question, but I've unfortunately no idea.
Because without that, it's a little bit about like those quotes at the very beginning you had about cheaper, better, faster.
That is true. That is true.
Who, a non-trivial amount of our annual budget is the solvents that we spend doing chromatographic separation.
I mean, the solvents in the final production step, they have two critical points. The one is that you use them, and usually you pump them away because you deposit and then you need to pump your glove box or wherever you do it. But the second point is that you keep some solvents in the solar cell, and that is a stability issue. So if you deposit dry, this problem is not there, yes. But
that's a performance. One's a performance thing, one's a green issue. The other question is, in your zoo of thiophenes, I've seen advances in your efficiency over time. The zoo seems to have pretty much the same animals that it's had for quite some time. Do you think that the future advantages are going to be more on the device fabrication or in the class of materials that you're playing with on new material development?
Both. You always need both. I mean, we really try to keep the backbone constant in this case, because our main goal was to really have these two different handles, electronic properties by backbone, length only, and a crystal structure by side groups, length and position. And however, in the meantime, we have also looked at some other molecules which had a different backbone. And clearly you see there's potential for improvement. But the other point is always that unfortunately, when you want to optimize the solar cell structure, the optimization is different for every molecule.
Karl, can you comment on the deposition rates and how they impact your cost analysis in terms of the manufacturing?
Yeah, we did some estimates, and the very simple message is if you do a roll-to-roll production and your band speed is larger than about a meter per minute, then you get from you have a tool depreciation range for slow speeds and a material limit for higher speeds. And when you are above about a meter per minute, you get into the materials cost limit. And at the moment, we have reached rates which give about this 1 meter, and I would personally expect that in the long-term production, we will be at a level of several meters per minute. And then the tool cost is a few %, and the materials cost dominate the production cost.
Which deposition step limits it to about 1 meter per minute?
Well, the very big issue when you do such a roll-to-roll process is you have 10 sources, and since you cannot go forth and back, you have to have the rates adjusted that every layer thickness is correct. And the material which has the smallest budget, what we call thermal budget, between evaporation temperature and decomposition temperature is limiting the rate. So you know that the materials there are some materials which have a kind of 200-degree budget. You know, they evaporate at 200 degrees and decompose at 400. But there are also materials which evaporate at 350 and decompose at 400. And those materials limit the process. So one of the challenges is to search for materials which have a very large budget between start of evaporation and decomposition. And that has also proven to be difficult.
No further questions? So before we thank Karl again, I'd like to make two announcements. The first one is that we are inviting and expecting all of you for the reception, during which you'll have also an opportunity to ask further questions to Karl, and then we'll be on in the atrium on the second floor. And then since Karl has lost his suitcase, we want to make sure that he has something, to put his hands around. And so Karl, as a small token of our appreciation, we'd like to see you go back to South Asia with this small present.
Thank you.
Thank you again.
Yeah, I'll try not to lose it. Thank you.